I did last time, since I forgot a couple of comments that would be useful. So again, if we have a periodic operator h and we decompose it into direct integral of operators h of k depending on the quasi-momentum k, then the Bloch variety of this operator is a set of points k lambda. I allow them to be complex such that this equation on the torus has non-zero solution. And we discussed first of all that analytic structure, this is not just a set, it's analytic set. Actually it's the set of all zeros of an entire function of some certain exponential order. We discussed the reducibility, structure of extrema, and other things, but I wanted to return to this topic. You remember when we discussed whether it's irreducible or not? It's a hard question, and it's proven that it's irreducible only for 2D Schrödinger operators. There is a simpler question, whether irreducibility means that it doesn't split, this Bloch variety doesn't split into two or more independent analytic surfaces that have no knowledge about themselves, about each other. In other words, irreducibility means that if you take any small open piece of the surface, it will determine the whole thing. That's irreducible. If it's reducible, it will determine only its component, but not other components. And the simpler question, as we will see, very important one, that's why I listed the whole bunch of names, including people here in the audience, who were proving this absence just of flat components. If there is a flat component, it's a reducible case, but this is a very special reducible case. And let me show you the original things that Thomas did in the simplest situation when he proved that the Bloch variety of periodic Schrödinger operator, and I will assume more than he assumed, for instance, that the potential is bounded. It's the easiest thing to do. That if you look at the dispersion relation of this operator, then there are no flat pieces. And as we discussed, due to the analytic structure of Bloch variety, if there is even a small flat constant piece, lambda is constant, then the whole complex hyperplane lambda equals constant should be here. And the idea is, if you want to prove that this is not happening, you try to go far away in the domain of complex quasi-momenta. And let us do this. So the idea is, we will refer to this idea a little bit further in a different circumstances. So the idea is, so what we need to do, we need to take this operator delta of k, the Bloch component. I will write it down again, we did this before, for quasi-momentum k, plus v of x. And then we will start changing k. And the idea is that if you act on L2 function by this operator, v, potential v can only increase the L2 norm by constant, since v is bounded. Actually, don't have to be bounded, but that's the simplest. So the power of increasing the norm of a function in L2, v doesn't change, it doesn't depend on k. And if we can find k such that this part, minus delta of k, increases the norm of functions to which you apply, with bigger constant, they cannot cancel. So, in other words, if you find k such that applying to any function in L2 on the torus, this thing has much bigger norms than that, it shows that they cannot cancel. Actually, when we will be discussing gaps, we will see a similar consideration, but where potential will have some parameter, and we will see that with some values of this parameter, this thing will be much bigger than that, and they cannot cancel. So, but that's later. And so you don't need even to look at this part. What you do, you look at this expression, and you want to have the following. You want to be able, given any constant c, no matter how big, you want to find k in Cn such that the following inequality holds. That L2 norm of delta of k applied to u is bigger than C norm of u in L2. Then picking this constant b bigger than the norm of the potential, we see that the only way they can cancel if u is 0. So you will show that for this k, there is no non-trivial solution of this equation. You can ignore lambda. Lambda can be absorbed into potential. Okay, so it's only about this computation. But now it's pretty simple. As soon as you have this idea to go into complex domain, which Thomas suggested, the rest is pretty simple in this case. Namely, first of all, your function is periodic, so it can be expanded into its Fourier series in x, its function of x. And since delta of k is constant coefficient operator, what it will do, it will just, at each frequency, it will just multiply with the coefficient by certain constant. So what we need to show is that this constant, all of those constants simultaneously can be made arbitrarily big by choosing delta of k. But now let's recall what delta of k is. It's minus delta minus 2ik dot gradient plus k squared. And now let's take k complex, k1 plus ak2. Then if you, here gamma is in the n, in this n. So if you apply this operator to that term, we don't need to carry the whole series, it's term by term calculation. What you will get what is the coefficient that will pop up here. It will be gamma squared plus 2 k dot gamma. You have to check that I am not lying, since I am proud to do this. Okay, plus k squared. Now if you expand into real and imaginary parts, this can be written as follows. It's gamma squared plus 2k1 plus ik2 dot gamma plus k1 squared minus k2 squared plus 2i k1 dot k2. And now let's just look at the imaginary part of this coefficient. If the imaginary part is large,
minus kappa squared. Before you go in the original place, isn't it minus kappa squared?
Because minus delta becomes.
Well, that's fine. That's fine.
Fine.
no, minus delta becomes
Plus
gamma squared.
That I'm not worried about. I'm worried about the last term. Isn't
The last
that
one is
minus
okay.
kappa squared, not plus kappa squared?
This
That
plus
I
k
kappa
squared.
squared?
Yeah, it's plus. It's plus.
That's correct.
Since we have,
You're right. Okay.
this expression. Also, it wouldn't matter, but it's a Z2 invariant. So if you take the imaginary part of this thing and make it large, then the whole thing will be large. And the imaginary part is pulling out 2. We have k2 times gamma plus k1 times K2, or it's K2 dot gamma plus K1. And now what you need to notice that this gamma, K1 and K2 are at your disposal. K2 is the imaginary part. This gamma only runs through the integer lattice. What you do, you pick K1 outside of this integer lattice, then this vector cannot get to 0. And what you do with K2, you take it large. Actually, it's easier to see if you can do this on one single component of. So you can think that K1 and K2 are scalars, and gamma is integer. Then if you take K1 half integer and K2 large, that's it. Those coefficients are large. You can make it arbitrarily large, picking large K2. And that's it. It shows that if you go far into complex domain, K1 plus I K2, so K1 on the only worry is that it's not on the lattice, and K2 is large. You can do this. You can make it arbitrarily large. That's it. So this shows that we don't have this flat piece that goes all the way to infinity. And since we proved that this is a set of zeros of an entire function, if there is a flat piece, it has to go to infinity, and that's it. Sorry. Another comment which it was reminded me last time, I will repeat that I was discussing the location in K-space and the non-degeneracy of extrema of band functions, so near the end of the spectral band. And I said that it was a big issue in both ways. There is one exception, that if you take lambda 1, the lowest eigenvalue, then it always behaves like this. It's always parabolic, and the minimum is that k is 0. Parabolic is not that it's exactly parabola. It means that the Hessian is non-degenerate. And this is a result by Kersh and Simon. Certainly, if you include magnetic potential, things will change. But without magnetic potential, so this is unquestionable. And there are many results, spectral results, that can be done below the spectrum, and it's hard work to make them work inside of gaps. And I will give you examples later. Okay, that's another comment. And another thing that I think is worthwhile mentioning is that sometimes I remember I had confused questions about this. And it's important to understand that after Fouquet transform, if you have function in HS, so it's a smooth function, then its Fouquet transform will belong to L2 on the torus with values in this rotating subspace in HS, in a section of a bundle. So what I want to emphasize that the smoothness from here doesn't translate to smoothness with respect to quasi-momentum. You have just L2 with respect to quasi-momentum. And it's useful since, for instance, in expanding into generalized into Fouquet eigenfunctions, you would need to chop this to pick several pieces of the torus and split L2 on the whole torus into L2 on sub pieces. And you can do this safely since there is no smoothness condition at all here. You get smoothness with respect to K only. It's like in standard Fourier series, you get smoothness on the torus. It means that you should have appropriate decay in the original space. Therefore, function should be not just in HS, it should be in HS and also decaying somewhat. For instance, if it decays exponentially at infinity, you will get analyticity. But without that, this smoothness doesn't translate to smoothness with respect to K. So, for instance, if you want to split this space into orthogonal sum of two subspaces, you are free to do this. Pick one measurable subset in T star and its complement and split into two L2 spaces. There is no issue with this at all. Another thing that I wanted to mention that also people sometimes ask this, that the fact that H of K, this sometimes is called Bloch Hamiltonian, depends on K analytically, it has nothing to do with the smoothness of coefficients of the operator. It is just, if you look at the Laplacian, which I just erased, you see that it's polynomial with respect to K. So smoothness coefficients doesn't have anything to do with analyticity with respect to K. Smoothness coefficients is needed only for one thing, that this operator on the torus is elliptic, is Fredholm. But there is no issue with this analyticity doesn't come from smoothness coefficients, which is what people sometimes ask. So these are some comments concerning the previous, what we did. Now we need one more object to introduce. This is something that you can find in every book on solid state physics, with zillions of awful or beautiful pictures, whichever way you look at them. There are books just called Fermi surfaces, etc. So what is a Fermi surface? So we have our dispersion relation, which is this graph that is always conveniently erased. I always erase something that I will need next second. So we have this dispersion relation. Fermi's surface is just a level surface of this multiple valued function. So what you need to do, you need to fix a spectral value lambda, and you take the level surface of, so let's say this is K two-dimensional. So you project this here, you get some level surface in the K space, and it is the Fermi surface at this energy level lambda, or spectral level lambda. That's what it is. So for each lambda, you have a level surface of this multiple valued function, and it is the Fermi surface. Truthfully, in physics, there is only one Fermi surface, since there is one special value of energy which is of interest. It's so-called Fermi energy, and so physicists are interested in essentially in one level. But we will not discuss this. For us, it will be important to allow this section at any level. So this is Fermi surface. So in other words, the definition is that you fix lambda and you consider all K such that those points in Bloch variety, or this is the definition. It's exactly like the definition of Bloch variety, except that we fix lambda, unlike in the definition of the Bloch variety over there.
Lambda could be complex.
Yes, but actually for us, I don't think that we will need complex lambda anywhere, except. And then, since the whole B sub H, the whole Bloch variety, here this calligraphic B I called the Brillouin zone. If the whole Bloch variety is a set of zeros of entire functions, it's also a set of zeros of an entire function of K. It's just restriction. Now, just to scare you, this is Fermi surface of one of the materials. By the way, online you can, if you Google, you can find fantastically beautiful library of Fermi surfaces of all crystal. I think this is maybe niobium. I don't remember what it is. And you see, it looks pretty complicated. But I remind you that even in free space, you can get complicated pictures. If you try to figure out, remember in free space, you take paraboloid and shift it periodically, and you just look at one brilliant zone, you have all those pieces of all those paraboloids. If you try to cut them with a constant level surface, you will also see pretty complicated picture. It will not be like a sphere. So it's very easy to get complicated. And physicists claim, I don't know how they do this, but they claim that they can observe Fermi surface, they can find it, and it determines most physical parameters. Well, I cannot comment on this. I just believe physicists. Now, what about its properties? There is a conjecture, which may or may not be true, that you remember we had conjecture that Bloch variety is irreducible. Then the conjecture is that the Fermi surface is irreducible, again, modular shifts that you have to eliminate, for any real lambda, or maybe for all lambdas except a discrete set. Well, I hope that smart people in algebraic geometry and analytic geometry have such a theorem that if the whole Bloch variety is irreducible, then almost every section is irreducible, but it's bad science there. Not only they don't have such a theorem, they have counterexamples. So you can have irreducible Bloch variety, but it's conceivable that all sections could be reducible. There are examples. Although, if we were allowed to tilt a little bit the direction of those cross sections, instead of being completely horizontal, if we could shake it a little bit, generically we will see only irreducible components. But who knows, maybe this fixed lambda direction is exactly the bad one. So it's still open question. You will see that irreducibility of this Fermi surface is closely related to possibility or impossibility of embedding impurity eigenvalues into the absolutely continuous spectrum. So that's why we care about it. This is proved for discrete, only for discrete Schrödinger operator, only on Z2. And by the way, the proof, which is due to Giesecker, Knörrer, and Trubowitz, takes a book of algebraic geometry with results by Deligne used, etc. So it is hard labor. There are some trivial cases. For instance, if you have a separable potential, if your potential, if your period, a group of periods is Zn, and potential is the sum of potentials of x1, x2, etc., it's easy to do this by hand and convince yourself that it's true, it's always irreducible for several potentials. A little bit less trivial thing is that in dimension 3, and again, if your lattice is exactly this as a coordinates along the periods, if your potential is not completely separable, but if it separates into potential of two variables plot 1, you can also prove that it's irreducible, invoking the result by Knörrer and Trubowitz about Bloch variety. So it should be true, but who knows? And whenever it's true, it's very hard. Unless you have separable potential, even this thing is hard since it refers to hard result by Knörrer and Trubowitz. So these things are very hard to verify. But unfortunately, it looks like they are germane to spectral theory. One other comment. It's often useful, and somehow very frequently I see that people kind of neglect this possibility, that instead of, besides analyticity with respect to spectral parameter and quasi-momentum, we have more variables. For instance, we could consider the potential as a variable. Let's say L infinity, and V belongs to L infinity. And then we can introduce the Bloch variety, which depends on K, which contains K lambda and, say, potential. And the whole thing that we had about analyticity with respect to those parameters, it's actually analytic with respect to those functional parameters, with respect to potentials. Indeed, how does the operator depend on potential? Just linearly. So there is nothing more analytic than linear function. And so those things, very often it's convenient to see this analyticity in the infinite dimensional space that includes also parameters of your operator. And it's not hard to do. The Weid's meta theorem, since I don't specify what are exactly the parameter spaces. For instance, for Schrödinger with electric potential, this space would be, let's say, L infinity, or some other suitable space of potentials. And then the whole thing, the Bloch variety and Fermi surfaces. So you see, you will have to include here K lambda and potential, such that h of k with this potential minus lambda u has solution on the torus. And it will be analytic subset in this infinite dimensional space. I will not show you examples of usage, but it's nice to have it in mind. Very often it saves a lot of work. Now a little bit about inverse problems. Of what kind? What is Bloch variety? Bloch variety is actually some fine structure of the spectrum of periodic operators. And the spectrum itself is just the union of intervals. And how much can it tell you? Bloch variety, it's very fine structured. It gives you details. It actually expands into representations of your groups of periods. So it's more fine information about your operator. And now the question is kind of inverse problems, like Barry mentioned. For instance, if I give you Bloch variety, can you recover the potential? Probably not practically recover, but is it uniquely determined, etc. So all kinds of problems like this. There is a famous Borg theorem in 1D, which says that the following three things are equivalent. I'm not sure about one of them. It's definitely in paper by Avron and Simon. I don't remember whether Borg has this. The following three things are equivalent. The potential is constant. There are no spectral gaps. And there exists an entire function whose graph is inside of the Bloch variety. You see, the Bloch variety is kind of big, multiple valued graph. It's conceivable that there is nice entire function analytic whose graph is part of this. For instance, in free space, this is just paraboloid. And those three things are equivalent. Now, this is kind of inverse problem type theorem. That if you know that there are not gaps, potential is constant. Now, this usually in Borg theorem is quoted in these two ways, that 1 is equivalent to 2. But it's a bad way to formulate it, since in dimensions higher than 1, it is just miserably fails. It just miserably fails. We will see that, and probably many people in the audience already know by heart, that in higher dimensions, you might easily have no gaps at all, and potential doesn't have to be constant. So this thing just completely fails in higher dimensions. However, there is a conjecture that the other two statements are still equivalent. That having potential constant is the same as having entire function with graph sitting in the dispersion relation. And it's proven in 2D only by Knörer and Trubowitz. Again, it's not a simple theorem to prove. In 1D, it's pretty simple since all those singularities come from the gap ends. You have some branching there happening. When they collide, those singularities go away. You can go through analytically and you can have analytic branch. But the same is true. Conjecture is that it's true in any dimension, but it's proven only in 2D. So this is the correct analog of Borg's theorem, not the standard formulation with 1 being equivalent to 2. Now, what you can easily notice that there could be different potentials that will give you the same Bloch variety. For instance, if you shift the potential, it will not change anything. Or if you change the sign of one or more coordinates, it will also not change the Bloch variety. It's very simple to check. Therefore, you cannot have complete uniqueness, since there are some natural symmetries that are allowed. So the question is, does the Bloch variety determine the potential up to those symmetries? And there is a theorem, again, only for discrete Schrödinger operator, only on Z2 lattice. And the claim is that there exists, you have two potentials, V1 and V2. And you want to know what happens if their Bloch varieties are the same. So the claim is that there is the Zariski open set in L2 on this torus. What is Zariski open set means that it's the whole torus except an algebraic subset. The bad points are algebraic subset. Such that if the first potential in this Zariski open subset and second potential is any, and if the Bloch varieties are the same, then potentials are the same up to natural symmetries. Again, this is the subject of the same book. So this whole book, Algebraic Fermi Surfaces by Giesecker, Knörer, Trubowitz, is tour de force of algebraic geometry. And in particular, they managed to prove this, but not, it's just Z2 discrete Schrödinger operator. No more than that. Thomas Kappeler proved analog of this for higher dimensions. Now, if you look at truly Schrödinger operators, minus delta plus V of x, there is very little known.
Peter, could you turn the mic on? I think it has been turned off.
What?
Mic is off.
Now it's on. So I don't know how it went off. If you look at non-discrete, at continuous version, there is very little known. There are wonderful papers in the middle of 80s by Eskin, Ralston, and Trubowitz addressing this. They are also tour de force of trace formulas and microlocal analysis and whatnot. And as a result, they proved some analogs of those theorems, but the analogs are much weaker. The statements are much weaker, and requirements on the potentials and on the lattice are much stronger. So, for instance, they don't have actual theorem like in this discrete case that if you have two potentials, then there are those two families of natural symmetries, shifts and discrete set of changing of sign. They proved under very kind of strong conditions, they proved theorems of the kind that if your potential is in some open set, and if the block varieties are the same, then they are the same up to a finite number of possibilities plus continuous family of like changing of sign and shifts, but it's not specifically determined what are those finite number of choices.
Again, mic problem. I think you are not being recorded when the mic is off.
Oh, again off. I don't know, it goes off by itself. It was on, but then it dies. I can yell. At least my wife claims. So the thing is that these are very complicated papers. I even won't try to present the results, since to formulate the results already would take some time. But I recommend you, if you are interested in such things, to look at those papers. And since then, essentially, as far as I know, no progress has been made. This is an outstanding problem about inverse problem or Floquet rigidity. If you fix like block variety, what can you say about possibilities for potential? So this is kind of widely open thing. Okay, and now finally, I've been talking about anything but spectral theory so far. So let me go to spectral theory, and you will see that all those analytic issues play their role. So brief content, I will talk about spectral gaps, very briefly about L2 eigenfunction expansion, which is very simple thing. Then I will discuss types of spectra, absolute continuity of spectrum. Oh, it died again. Density of states, variety of type of theorems about expansions into solutions, about testing spectrum by generalized eigenfunctions. I want to talk about Vannier functions, and it goes off by itself. And Liouville theorems also. So let's look at band gap structure first. And I created a table comparing one-dimensional and PDE situation. So about overlaps. There are no overlaps of bands in N1, in N more than one, overlap is a norm. About gaps, according to Barry-Simon's theorem, generically all gaps are open. Thank you. In n bigger than 1, there is an open set of potentials which don't have any gaps at all. If there are no gaps, Borg's theorem says in n1 that it's constant potential. Actually, in dimension higher than 1, any sufficiently small potential has no gaps. Now, let's look just at the free operator. In the free operator, minus second derivative in dimension 1 and minus Laplacian, the situation is that the bands, which are easy to compute, at least to understand where they are, they touch each other and cover the whole positive semi-axis. In the higher dimensions, they also cover the the whole positive semi-axis, but they overlap, and they overlap more and more the further you go along the positive semi-axis. And this is what, for instance, Paranovsky and Sobolev have spent a lot of time and work studying. It is actually number theory problem about this overlap. And I remind you, it's about a free operator without any potential. So it shows that situation is very different in n equals 1 and n bigger than 1. Now there is this, let's talk about gaps. There is Bethe-Sommerfeld conjecture that in higher dimensions there are always only finitely many gaps, maybe none at all, in the spectrum of periodic Schrödinger operator. And by now it has been proven in full generality, and the important works by these people. It's an alphabetical order, it's not historical order or any.
T comes between D and P?
Dalberg and Trubowitz, they were co-authors. Okay. Keep doing this, I have no objection. Actually, maybe I should say that original progress was made by Skriganov, who proved this with some significant arithmetic restrictions at the lattice. Then in dimension 2, Dalberg and Trubowitz proved this without restriction on the lattice, but only in dimension 2. And Paranovsky and Sobolev, by now, they have finished this thing completely, which is a really difficult, amazing work one needs to do. So one can ask whether the stronger conjecture holds. I don't know whether you can say that this is true for any second order periodic elliptic operator, whether it's true for periodic waveguide problems, etc. And something is done in this regard again by Paranovsky and Sobolev, mostly, that if you have operator of this type, so lower order terms could be periodic. For instance, you can include periodic magnetic potential, and this is mostly work of Paranovsky and Sobolev, with also contributions from these mathematicians. Now, if you look at graph problems, this conjecture fails miserably. It's easy to construct examples of periodic graphs with infinitely many gaps. And I will actually tell you how to do this. Now, so this is Bethe-Sommerfeld conjecture says that you expect only at most finitely many gaps. Now there is a situation when you expect to have no gaps at all. So what is the situation? It's the following. If we consider the standard covering when Rn is wound in the torus, the deck group of this covering is the n. We quotient the n. And the n happens to be the first homology of the torus. Now, this is what is called maximal abelian cover. So this covering can be understood as follows. You can take the torus and first take universal cover. You probably all know that there exists universal cover, which has zero fundamental group. Then that group of this universal cover is fundamental group of the torus, which is non-commutative group, very much non-commutative group. But if you make it commutative, is you quotient the by commutator subgroup. Quotient of P1 by commutator subgroup is exactly H1. You will get what is called maximal abelian cover. So standard Rn on the torus is maximal abelian cover of the torus. So this is the general definition. If you have a compact manifold X, and if you have covering, I will say the word, but I will not explain unless you insist, normal covering of this X, whose group is exactly H1 homology of X, then, and again, you can consider it, you can first take the universal covering, the simply connected covering of X, the universal covering, and then quotient out the non-commutative part. So this is called the maximal abelian covering. Since one can show that if you have any abelian covering of X, it could be put here in the middle, that Y will cover this covering and then it goes to X. So all other abelian coverings are somewhere in between. You quotient Y about something, you get smaller subset, then you quotient more, you get X. And that intermediate thing is abelian covering. That's why it's called maximal abelian covering. An interesting thing is, I tried to check, I'm not sure whether it's due to Sunada or Bob Brooks, that if you have a covering of Riemannian manifolds and the group is amenable, in our case it's abelian, so it's amenable, then the spectrum of X is part of the spectrum on Y. So when you take a covering of a compact manifold with an amenable group occurring, if you don't know what amenable is, we need only abelian group, then the spectrum on Y is bigger than spectrum on X, at least not smaller. In other words, if you take abelian covering, you increase the spectrum. Again, I don't remember whether originally it's Sunada's or Brooks theorem. So now, if you look at Laplacian on the maximal abelian covering, its spectrum will be the biggest among all abelian coverings. The spectrum is biggest, the gaps are smallest. The natural conjecture is that there are no gaps at all. That if you take maximal abelian covering of a compact Riemannian manifold, then the spectrum of a Laplace Beltrán operator on this covering has no gaps whatsoever. In other words, any gap can be removed by some abelian covering. Well, it's not proven. It's not proven. It's very plausible, but it's not proven. There is analogous conjecture for graphs. For graphs, you have to assume that the graph is regular. There are reasons why. Otherwise, it's not true. Regular means that the degree of each vertex is the same. And then the graph can have either even degree or odd degree. For it is proven for all graphs of even degree that if you have compact graph of even degree and you take maximal abelian covering, you have no gaps. Without the word maximum, it's not true. If you just have an abelian covering, it might have gaps very well. For odd degree, it's not proven. There were several cases when some Japanese mathematicians who actually proved for even degree, proved this for various examples of graphs of odd degree. I also proved this for various examples of graphs of odd degree. The simplest is K4, when X is a complete graph with 4 vertices. It's the simplest odd degree graph. In every case I tried, I could prove that there are no gaps. But I couldn't make it work in general. I couldn't make. So this is no gap conjecture. So far we were going in the direction of killing gaps. Finitely many gaps, no gaps. Now, how can we create gaps? Since there are cases when we need gaps. For instance, semiconductors are semiconductors due to presence of gaps. we don't create semiconductors. Nature created them. Fortunately, they have gaps. But when, for instance, you create materials like photonic crystals, you are playing the god. So you have to create it in such a way that there are gaps. So what are the methods of creating gaps? Well, for Schrödinger operator, there is a very simple method of creating gaps. So you take, let's say, even free operator, that is spectrum, and what you do, you start adding, this is X space, this is lambda. You create a deep well, potential well. If you create potential well, what you normally get, you get an isolated eigenvalue below the spectrum. So you see, you already have a gap, but it's not periodic potential. So what you do, you spread those wells periodically, but at very large distances. So there is very little tunneling, but there is some between them. And this will lead to this eigenvalue spread into a small band. And okay, here you are, you have a gap. And the issue why we can do this is that we can move the bottom of the spectrum. By creating potential well, we can shift down the spectrum. Well, it's not possible, for instance, for operators like Maxwell. Maxwell operator, no matter what you do with the medium, the bottom of the spectrum will be always at 0. So this is not possible. On the other hand, the Bethe-Sommerfeld conjecture says that you don't expect gaps if you go far up. So you don't have gaps below, you don't have gaps far up. So you, for Maxwell, meaning, for instance, photonic crystals, you have to open gaps somewhere in the medium range.
Even Maxwell, classically, it's not sign definite. The spectrum is unbounded.
Oh, yeah, I mean the second order version.
Right, Maxwell squared.
It's curl 1 over periodic function curl. This is operator.
Squared Maxwell.
Yeah. It's second order. It's squared. Okay. So that's why I mentioned it already in the beginning of 90s. Photonic crystals bite the dust. Beat the dust. So. Since it is hard to create gaps here, and if you allow periodic manifolds, you can create manifolds with gaps, again with finitely many, by making the geometry very high contrast. For instance, large bubbles connected with long thin tubes, such structures. So high contrast geometry, and you can do this, it's not very hard. And in Maxwell, as we showed, you can create gaps if you also use high contrast approach. If you use optically dense materials in the air, things like that. Playing with high contrast, you can open gaps in Maxwell as well. But the bottom line is that creating gaps, and especially creating gaps at a prescribed location in the spectrum, is extremely hard. And so far we were discussing the gaps that arise due to periodicity. And it's almost impossible to control them. You want to create the gaps of this side at that location, I don't know how to do this. But actually, there is a different mechanism which has nothing to do with periodicity, but can be used in periodic media as well, which allows you to open gaps. And this is resonant gap opening. What it looks like Oh, I have a minute, so I'll say something. So this is, the idea is that you take your medium, you spread throughout this medium small identical resonators. And what happens, the idea is that near the eigenfrequencies of those resonators, the medium should have spectral gaps. The idea is the following, that what I mean spectral gap, you cannot have wave of this frequency. So the idea is that you send waves through the medium, it starts exciting those resonators, and it cannot propagate since it takes infinite energy to do so. So this idea was suggested. This allows gap manipulation since it's up to you which resonators to use. It was suggested by Pavlov, maybe by some people before that, but I think it has never been made rigorous in continuous setting, since it's really hard. Even on graphs, it is also hard. It was done on graphs, on discrete graphs by Eisenman and Schenker, and it's not hard to translate it to quantum graphs. And here is the picture. Explanation I will give you tomorrow. But the picture is like this. So you have a graph, this is underlying graph, it doesn't have to be periodic, and you have additional graph decoration, like this sword. And you attach this decoration to every single vertex of the underlying graph. Then it's not hard to prove, and I will show you the proof next time. It uses the same idea that you will have two terms in your equation. One is large, one is much smaller, and so you cannot have solution of your. You cannot have solution in near this region of lambdas. So one can show that this creates gaps, and actually this is an example of an antenna that was built due to progress in photonic crystals. With the main purpose is to have a spectral gap, and you see it kind of resembles this. Those little mushrooms everywhere, except that it is done in continuous medium. I don't think we have any rigorous result about the continuous medium, but it's the same type of effect. But I will discuss it tomorrow.
Regarding your very last remark, I thought that isn't what, as I'm sure you know, first Hempel and Lee now, right? Example of gaps, and then Zhikov independently from point of view of homogenization.
And again, these things are again playing on stuff. I will mention this, right. But they playing on things like high contrast in some parameters and.
But essentially, what is behind this is some kind of local periodically distributed resonance.
Yes, yes,
right?
yes.
And the gaps open near the eigenvalues of this type.
Yes, I definitely know right. This, and
and it is rigorous.
Yeah. But it's still kind of asymptotic result. Asymptotic result when some parameters go here and there. It's again something of the nature like we did with Figotin. But
what do you mean by not asymptotic, but like a rigorous result in which sense?
Oh, it is rigorous result, but it's asymptotic. Then if you take those parameters to that limits, in the limits, that's what you will see. Yeah. But this decoration doesn't require any limits. You just put this decoration, you open the gap, and you know where.
You mean that those Hempel, Leonau, Zhikov, and others, this is example of asymptotic resonance, right?
Yes.
Kind of quasi-resonance.
That's what I mentioned, like I called high contrast. The same as Post and Hempel work on manifolds. They also use this high contrast, like take big bubbles with thin tubes, connecting them, and you can create gaps. It's not such.
It's the same as that tunneling phenomenon.
As what?
The tunneling on the blackboard over there.
Oh, okay. Yeah. That's exactly. that's the same. Except that it's not potential, it's metric you manipulate, but the thing is that one doesn't want to have those high contrast things, since usually, like what we did with Hygotin, we proved the existence of those gaps, but in unfeasible values of epsilon and mu in Maxwell. So we don't have such materials. So
you mentioned the result that in discrete 2D case you have an open set of spectrally rigid potentials, right?
yeah.
Yeah. So to which extent do you remember to which extent this set is precise, is explicit? So,
Which means the excluded set is algebraic. Whether they have explicit polynomials there, I don't remember.
whether they can actually produce some specific potentials that are rigid.
Yeah, but this is the question whether it says that you can take any potential except those on algebraic subset.
Yes.
So the question is whether they have explicit formula for polynomials defining this subset.
No, the question is whether they can produce something.
If you know this polynomial, you take anything which is not here, it will work. But I don't remember whether they have. It might not be that explicit. I don't remember, frankly. But you can look. It's hard to read that book. It's hard for me since I know next to nothing about algebraic geometry. But they had very nice, before the book, they have very nice survey paper which is called Overview of Algebraic Fermi Surfaces, which you can understand.
So if you start, because I'm here learning on this Anderson localization, if you start distributing these things not periodically but randomly, can you visualize this mysterious pure point spectrum type things for?
It's question not to me. You asked during a wrong lecture.
Okay.
You asked the person sitting in front of you. In other words, I don't know. To be honest.
Well, let's thank today's speakers again.